Okay, try to picture this. You're building a map of the cosmos, but it's not just a static picture.
Right.
You've got billions, literally billions, of tiny specks of light, all moving, shifting.
Yeah, like a massive dynamic jigsaw puzzle.
Exactly.
Yeah.
And Gaia, this amazing satellite, is just feeding us this constant stream of data about them year after year.
Mm-hmm.
So the big question, the one we're tackling today, using your source material, is how on earth do scientists take that deluge and figure out exactly where each star is and, where it's going?
It's a fantastic question. And yeah, this deep dive, it's really about giving you that shortcut to understanding the sheer cleverness behind processing all this Gaia data.
So getting right into the ingenious solution.
Pretty much. We'll unpack how they transform those countless little observations into, a coherent, precise map of our galaxy.
Okay, so boiling it down, Gaia scans the sky, right? Over and over.
Constantly.
So we get multiple snapshots of the same star, but at different moments in time.
And crucially, these stars aren't just sitting still. They're moving through space, proper motion.
Right, and then there's parallax, too. Because we're orbiting the sun, the star's apparent position seems to wobble slightly from our viewpoint.
Exactly. So over the months, the years, Gaia collects all these tiny shifts. Hints of motion, hints of parallax.
And sometimes even more subtle things, like if the star has a planet pulling on it or another star orbiting it.
Or even gravitational lensing, yeah. All these tiny effects are buried in the data. The ultimate goal, as the material lays out, is to pin down those key parameters for every single star.
Position, motion, the essentials.
The 5 or sometimes more astrometric parameters. But when you first think about this, some really practical questions pop up immediately.
Oh, for sure. Like, how do you even know you're seeing the same star again in a different scan months later?
That's a big one.
Yeah.
And what's your 0 point? What's the absolute reference frame for all these positions?
Yeah, and why the two telescopes? Why look in two directions at once?
Good question. Plus, how do you deal with the fact that the telescope itself isn't perfect? Tiny distortions.
And the satellite's own wobble and drift. That must affect things.
Absolutely. Now, all these are critical, and they are handled in the full processing pipeline. Huge efforts go into solving those.
But for today, we're zooming in a bit.
Exactly. We want to focus on the core logic, the fundamental strategy that makes tackling this whole immense problem even possible. What's the underlying principle?
Okay, so what is it?
Well, it boils down to this concept of a global solution. Think of it like creating a single self-consistent model for the entire sky observed by Gaia.
Okay.
So Gaia's detectors, the CCDs, they're recording thousands of star detections every single second.
Thousands per second. Wow.
Yeah. And the goal is to take all those measurements from all stars over the whole mission and solve for, at least those 5 key parameters per star.
Position, parallax, motion.
Exactly. While also solving for how the instrument itself changes over time. Tiny variations in its behavior. Ah, okay. So it's not just the stars, it's the instrument too.
Simultaneously. And this is where it gets, really elegant.
Oh, so?
Because the star positions, the instrument calibration, and the satellite's precise orientation where it's pointing, they're all tangled up together.
Interconnected.
Deeply interconnected.
Yeah.
And the key linking them is that fixed angle between Gaia's 2 telescopes.
Ah, the 2 fields of view. That's why it's important.
It's crucial. It creates this network across the sky. Seeing 2 stars separated by that known fixed angle provides a really strong constraint.
It ties different parts of the sky together mathematically.
Precisely. And what's really efficient is the calibration part. Because Gaia is always observing, they don't need separate calibration time.
Oh, right.
The calibration just sort of falls out of the science data.
Yeah.
It's continuously monitored and updated as a natural part of the process. No downtime needed just for calibration.
Okay, that makes sense. But still, billions of stars. You said hundreds of observations for each one.
Plus all those instrument parameters changing over time. Plus the satellite's attitude.
Yeah.
The sheer number of unknowns you need to solve for must be
Astronomical, pun intended.
Yeah, absolutely.
You've nailed the bottleneck. If you tried to write down one giant set of equations that included every single observation, every star parameter, every calibration parameter, every attitude parameter,
Forget about it.
you couldn't solve it directly. The computational problem would just be too massive, way too complex for even the biggest supercomputers to handle in one go.
So, if you can't just calculate the answer directly, what do you do? How do you even start?
And that leads us to the core idea, iteration.
Iteration, doing it step by step.
Exactly. Because everything is so interconnected, the only practical way is to solve it piece by piece and then cycle through, refining the estimates each time.
Like tuning an instrument. You adjust one part, see how it affects the others, then adjust another.
That's a great analogy. You improve your estimate of the star positions based on the current guess of the calibration and attitude. Then you use those improved star positions to refine the attitude estimate. Then maybe refine the calibration. And you loop around.
And this wasn't a completely new idea for Gaia.
No, the experience from Gaia's predecessor, Hipparcos, was really informative. Hipparcos faced a similar problem, just on a smaller scale. So the idea of an iterative approach was already there.
Okay. But scaling it up to Gaia's level, that must have been a huge leap. The source material mentions this was a big question mark back when Gaia was approved, around 2000.
Oh, absolutely. Proving that this iterative global solution was actually feasible for Gaia, that it would work computationally and mathematically, was a major, major undertaking.
Who figured that out?
The mathematical heavy lifting, the framework for how this iterative solution would actually work in practice, was largely led by Lennart Lindegren.
Ah, Lindegren. That name comes up a lot.
Deservedly so. His work, laid out in some key papers, provided the fundamental blueprint for numerically tackling this incredibly complex puzzle.
Okay, so let's piece this together then. We have this mind-boggling amount of Gaia data. Billions of stars, positions, motions. Direct calculation is out.
Impossible.
So they use this iterative method, the astrometric global iterative solution, AGIS.
That's the one, AGIS. It involves looping through updates for different blocks of information.
Like one block is the star parameters.
Yep. Positions, parallaxes, proper motions for all the stars.
Another is the satellite's attitude, its orientation second by second.
Exactly.
Then the instrument calibration, how the telescope is behaving.
Right. And maybe some other overall global parameters that affect everything.
And you cycle through these blocks, updating each one based on the latest estimates from the others.
Precisely. Because, and this is the key reason why iteration is essential, each block depends on the others.
Ah, right. You can't get the perfect star position without knowing exactly where the satellite was pointing.
And you can't know exactly where it was pointing without having good estimates for the star positions it was looking at.
It's a circular dependency.
It is. So you start with an initial guess, and each loop, each iteration, hopefully brings you closer to a consistent solution for everything. It's a continuous refinement.
It sounds like a really delicate dance, computationally speaking.
It really is. And your material rightly points out, just having the block iterative idea wasn't the end of the story. There were big questions. Well, would the process actually converge? Would it settle down to a stable, accurate answer?
Or just keep oscillating or drifting.
Yeah. And how many iterations would it take? Dozens, hundreds, thousands. How much computing power would that need?
And does the order matter? Which block do you update first?
Does the order affect the speed of convergence or even the final answer? And perhaps the most subtle question, is the solution you finally converge to the actual best fit? The true global minimum in a mathematical sense, or just a pretty good local fit?
Wow. Okay, so lots of devils in the details there.
Absolutely. Implementing AGIS was and is a huge software engineering and mathematical challenge.
And this core AGIS process, the astrometry part, it doesn't exist in a vacuum, right? Gaia measures other things too.
Oh, definitely. AGIS is the heart of the astrometric solution, but it's integrated within a much larger ecosystem of data processing.
Like what?
Well, Gaia also measures the brightness and colors of stars. That's photometry. Huge pipelines process that. It identifies binary stars and analyses their orbits. It measures radial velocities for millions of stars, how fast they're moving towards or away from us.
Ah, the spectrograph data.
Exactly. And it classifies objects. Is this a star, a quasar, an asteroid? All these massive processing tasks run alongside and sometimes feed into or receive information from the core astrometric solution. It's a whole interconnected system.
It's easy to just focus on the algorithms and the data volumes, but you mentioned Lennart Lindegren. There's a massive human effort behind this. The source mentioned the DPAC.
Yes, the Gaia Data Processing and Analysis Consortium, DPAC. It's a huge collaboration. Hundreds of scientists and software engineers across Europe.
Dedicated for years, decades even.
Absolutely. Pouring their expertise into designing, testing, running, and validating all these complex processing pipelines, transforming those raw signals from the satellite into the amazing science-ready catalogs.
And Lindegren's role was particularly significant.
Hugely significant. The source highlights his pivotal contributions not just to Gaia's AGIS, but stretching way back to the development of the data analysis for Hipparcos as well, a career dedicated to this kind of high-precision astrometry.
And that work has been recognized, right? Some major awards mentioned.
Yes, deservedly so. He received the German Astronomical Society's Instrumentation Prize in 2018 and the Brouwer Award from the American Astronomical Society's Division on Dynamical Astronomy in 2020.
Big honors.
Very prestigious. And the citation for the Brouwer Award is quite powerful. It says his work has changed our understanding of the universe at a fundamental level. And it goes on to say his contributions will have a lasting legacy for, generations of astronomers. It really underscores the human impact behind the technical brilliance.
That's incredible. It puts a face to the algorithms.
It does. It reminds us that these huge scientific leaps are built on the dedication and ingenuity of many individuals.
So thinking about this whole process, this intricate iterative dance to solve a problem that seemed almost impossibly large, it makes you wonder. This whole approach, breaking down a massive interconnected data challenge and tackling it iteratively, where else might this be happening? What other fields, maybe completely unrelated to astronomy, could be facing similar, too big to solve directly data puzzles?
That's a fascinating thought.
Are there areas in, say, genomics or climate modeling or maybe even complex social network analysis where similar iterative refining techniques are the key to unlocking understanding from overwhelming data? What other frontiers might be yielding to this kind of clever, step-by-step computational thinking?